In this video, we're now going to take a look at how to compute the slope of polar curves. So we have an idea of our polar coordinate system. We've seen a few interesting polar curves, but we really want to get to the meat of the matter, which is doing some calculations with these polar curves. So remember the standard way, kind of the explicit way of expressing a polar curve is by defining r, which is our radius, as a function of theta, which is our angle. So those are our standard polar variables, r and theta. Now, if you think about the slope of a curve, that's, one way to denote it is dy over dx. Well, dy over dx, it involves two variables that are not currently in our equation. This equation relates r and theta. So what do we use? Well, previously when we were looking at the polar coordinate system, there were a pair of equations that we can use to write down x in terms of r and theta and y in terms of r and theta. So recall that we have these two equations, that x is r cosine theta, and we can get that from our basic right angle or right triangle trig, and then y is r sine of theta. So over here we have the polar, and then on this side, because we have two separate equations, one for x and y, this is really parametric, right? So then taking this further, since I have an equation where I can replace r with this function of theta, here are the parametric equations for the same polar curve. Just replace each r with f of theta. So we have that x is f of theta times cosine of theta, and y is f of theta times the sine of theta, right? And again, let me emphasize what we've done here is we've started with the polar equation, and then we've now expressed that polar equation parametrically. And why is this helpful? Well, because we've done the calculus of parametric curves. We've done things like slope, area, arc length, and so forth, right? So let's now say, okay, once we have these parametric equations, what can we do? Well, we can write down the derivative of y with respect to x. And now, previously when we were doing our work with parametric curves, we used t as our parameter. If you want to, you can actually express this in terms of t. Just switch all the thetas to t. The theta is kind of like a dummy variable. It just happens to be a standard variable that we use for angles, right? But any old variable would work, provided we're not using that variable in another role. But I'm comfortable working with theta. I encourage you to get comfortable working in terms of theta, so we can actually write down what essentially will be a formula for the slope of a parametric curve. Or I'm sorry, well, this parametric curve, which just happens to be also this polar curve. So it would be dy d theta divided by dx d theta, provided that dx d theta is not equal to 0. Now, because of how these conversion formulas work, we're always going to end up with a product here. So unless f of theta happens to be a constant, where it doesn't depend on theta at all, because we have one function of theta multiplied by another function of theta, can you tell what derivative rule we're going to have to use? I hope you said the product rule, because that's exactly what we need. So I express the product rule like this. So it's the derivative of the first, which is our f of theta. So its derivative is f prime of theta multiplied by the second plus the first times the derivative of the second, and the derivative of cosine is, oh, actually what I'm writing down, I'm looking at the x equation. So this is actually going to be, let's actually do this. I'm glad I caught that. this, let me just kind of move it down a little bit because that's actually going to be the denominator, right? That's going to be our dx d theta. So I'm kind of setting up my fraction in a reverse way, but that's fine. So let's just do that. So the derivative of cosine is negative sine of theta. And then in the numerator now, take the y equation and write down its derivative. It's very similar, right? You'll have f prime of theta times the sine of theta, and then plus f of theta times the derivative of sine, which is cosine of theta, right? Now, as far as simplifying this, if you look closely, you'd think, man, surely there's something I can, use to simplify this expression. And quite frankly, there isn't, right? Because if you look at all four terms, there are four terms in this expression. None of them, there is no common factor, right? So many times when like if you were to search, for instance, the slope of a polar curve, you might see a formula like this. And since this factor of sine has a negative in front of it, I'm just going to use that negative and replace that plus sign and write it like that, right? So again, it's not the type of formula that you would think of, especially when you think of the previous ways that we've computed the slope of a curve. We never had to do anything like this, and this is because we now have a slightly different representation of the curve, right? So this is our formula for the slope of a parametric curve. I wouldn't really memorize this. I think it's actually easier to memorize the polar conversion going from r theta to xy and then do it parametrically and apply it then. So let's do an example just to illustrate this. And in this example, I'm going to use a fairly simple polar curve, and we'll do a few things. Let's find the slope in general, so kind of just the derivative function, and then let's use the derivative to find the slope at a particular point, and then let's find the equation of the tangent line at that same point. So here is the polar curve that we're going to use. Something really simple. R equals theta squared, and this, if you remember, one of the curves we looked at previously was a spiral. This is the spiral, but it spirals out more quickly than the one we saw in our maple visualization, right? So it's r equals theta squared, and then let's use this value of theta, one of our nice special angles, and we're gonna compute the derivative function, slope at this particular point, and the equation of the tangent line at this particular point. All right, so let's see how this works. So number one will be just computing dy dx. So right away, let's use our conversion formula. So x is r cosine theta, but instead of writing r, I'm going to write theta squared times cosine of theta. And then let's write down the corresponding equation for y. Similarly, it's r sine theta, but in this case, it's theta squared sine theta. All right. Then let's write down the formula for the slope, dy dx. So dy dx. Now I'm going to make sure I differentiate my y equation first. That one's going to go in the numerator. So the derivative of this product. So now that we have an actual f of theta, we can compute it. If you wanted to, you could sort of glance back at this formula and just kind of write down the terms, but I'm going to say it out anyway. So product rule will give us 2 times theta times the sine of theta, and then plus theta squared times the cosine of theta. Right, you can see the terms matching up in our formula there that I boxed off. And then in the denominator, you'll have 2 theta, this times cosine of theta, right? Derivative of the first times the second. And then I'll just go ahead and write down the minus theta squared times the sine of theta. And that's it. That's the derivative as a function, right? So as long as this derivative exists, when for certain values of theta, we can use it to find the slope. So let's look at number 2, where we're actually going to use this first derivative to find the slope of this polar curve when theta is pi over 4, right? So that's basically taking the derivative that we've computed and evaluating it at theta equals pi over 4. So wherever there's a theta, just replace it with pi over 4. Now, one of the reasons why I chose pi over 4, that obviously it's one of our special angles, right? You have things like pi over 6, pi over 4, pi over 3 in the first quadrant. Well, pi over 4 has at pi over 4, sine and cosine, those ratios are exactly the same, and it happens to be the famous root 2 over 2. So let's just plug those in. So we'll have 2 times pi over 4 times root 2 over 2 plus pi over 4 squared times root 2 over 2, and then divided by a very similar expression. And the reason why I say that is because, again, even though the cosine and sine functions are switched when compared to the numerator, the value of those are the same, root 2 over 2, and then we'll have the negative sign there. So you can almost just almost copy and paste, but then you have to change one of the expressions, or one of the operators here. So this is then minus, and then we have the quantity pi over 4 squared times root 2 over 2. So let's see how things simplify. So, I mean, you could see, let me, cross out some of the things that clearly reduce. So we have that going, and then similarly in the bottom, we have that going. Now with pi over 4, that quantity squared, it becomes pi squared over 16. And then we'll have root 2 over 2. So nothing's really going to reduce there, but let's write it down and see it. So we are going to have I'll put the root 2 first, so root 2 pi, make sure that the pi isn't under the root, and then that's over 4, and then I will have plus, so let's do a little bit of mental arithmetic here. The numerator is going to be root 2 pi squared, and then the denominator is going to be 16 and then times 2, so 32. All right, so it's going to be root 2 pi squared over, again, 16 times 2, 32. And then in the denominator, something similar. It basically just changed that plus sign to a minus sign. So root 2 pi over 4 minus root 2 pi squared over 32. Now what we can do to get rid of the, so right now we have a rather complicated looking fraction. We have several fractions within a larger fraction. Let's multiply the top and the bottom by the lowest common denominator, which in this case is 32. So if I multiply the top and the bottom by 32, this becomes 8 root 2 pi, and then I'll have plus root 2 pi squared, and then in the bottom, again, something very, very similar. We will have 8 root 2 pi minus root 2 pi squared. Now, we could have done this earlier. In fact, we could have done this here. Notice each term now has a common factor of the square root of 2. So we could actually factor and reduce using the square root of 2. So what do we end up with? 8 pi plus pi squared over 8 pi minus pi squared. Okay. But we also have a common factor of pi, right? Notice each of these expressions have a pi in them, so we could take it even further, factor reduced by the pi, and then we'll have 8 plus pi over 8 minus pi. And that's our slope. Now, if the next thing, if you wanted to take this further, is to get a decimal approximation. I'm not going to do that. I like this number. It's a pretty cool looking number. 8 plus pi divided by 8 minus pi. So that's our slope. Now, third question. What if we wanted the equation of the tangent line to this polar curve? In fact, let me write the curve again so I don't have to scroll up. And again, we want it at theta equals pi over 4. Well, this number here represents the slope of the tangent line. So what we need to do is to find the point that the tangent line passes through. Now, we have two ways to represent that point. We could do it in polar form, right? But we don't really know the equation of a line in polar form. We could figure it out, but it would be a lot easier to express the equation of the tangent line in the rectangular form using x and y instead of r and theta. So in order to do that, we need to find the value of x on this polar curve when theta equals pi over 4. So again, we're going to use the same conversion formula. X is r times cosine of theta, so we have that. And then similarly y. So I'm just writing down what we did earlier. And then now we need to find the value of x when theta is pi over 4. And if we plug it in and do similar calculations, we will have pi squared over 16. And then the cosine of pi over 4 is that root 2 over 2. So again, we get a familiar expression, right? So I'll put the root 2 first, and then the denominator is 32. And it turns out the y value at this point is going to be exactly the same, right? So there's a nice symmetry there. So it will be pi squared over 16 times root 2 over 2. I guess I could have just written down the result that I had in the previous line, or have in the previous line. But there you go. So that's our ordered pair. This is our slope. Here is the equation of the tangent line. And I'm going to leave it in the point slope form. I'm not going to worry about doing any kind of crazy algebra to get it in the slope intercept. So it's y minus the y value, which again, same as the x. So we got root 2 pi squared over 32 is equal to our slope, which is this quantity. I'm going to put it in parentheses just to make sure my expression implies the correct order of operations, and then x minus the x value, right? So you can see it's not the, well, I mean, beauty is in the eye of the beholder, but some people might say this is not the prettiest equation. I think it's pretty cool. But so here we have the equation of the tangent line of this polar curve at this point, but this is in the rectangular form because this is an easier, more convenient form to express the line for us. All right, and there you go. So that's the story behind the slope of a polar curve. It really boils down to going from the polar to the parametric form, and then we can do everything that we know about parametric curves. So hopefully you found this interesting. It was my pleasure showing this to you, and I'll see you in the next video.